Imagine hiring a world-class author, but you force them to write their masterpiece using a child set of pre-made rubber stamps.
Yeah, that's a great way to ruin a good book.
Right. But for years, that is exactly what we've been doing to multimodal models by forcing them to use frozen VAEs. So today on AI Paperslop, we are looking at a June 2026 paper titled Representation Forcing for Bottleneck-Free Unified Multimodal Models.
And this is from researchers at ByteDance Seed, the University of Hong Kong, CUHK, and others.
Exactly. And the core insight here is that for unified multimodal models, or UMMs, rely on a separately pre-trained frozen VAE for image generation, creates this hard structural bottleneck. It just heavily limits the output quality.
But the catch is, if you naively switch to direct pixel space generation, you get a massive quality drop.
Absolutely massive, because the models basically struggle to learn both the high-level semantic structure and the low-level pixel details at the exact same time.
Right. And the breakthrough in this paper is a technique they call representation forcing, or RF. By forcing the model's decoder to autoregressively predict high-level visual representations as intermediate tokens.
Like before it even generates the pixels.
Yes, exactly before the pixels. It effectively creates this in-context structural blueprint, and this completely bypasses the external VAE.
Which is wild because it actually matches state-of-the-art VAE generation metrics.
Yeah, and it even improves the model's overall image understanding capabilities.
So if you're a practitioner listening to this, imagine you want a truly end-to-end multimodal model, but you've been stuck duct taping a frozen VAE to the back of your transformer. This deep dive is going to show you how to rip off that tape.
It really is about teaching the transformer to generate raw pixels purely by grounding it in its own understanding representations.
So let's get into it. To understand why representation forcing is even necessary, we first need to look at why the current standard for UMMs is, well, fundamentally broken.
Or at least fundamentally limited. I mean, look at state-of-the-art models like Chameleon or ENU3.
Or Transfusion and Janus Flow.
Right, all of those. They've all successfully brought text and image generation into a shared transformer backbone, which was a vital step forward for the field.
But they still rely on a vision autoencoder.
Yeah, whether that's a continuous VAE or a discrete VQ-VAE, they use it to compress high-resolution images into a more manageable latent space.
And the fundamental problem with that approach is the objective function the VAE was originally trained on. A VAE latent space is optimized purely for reconstruction.
Exactly. It uses losses like mean squared error or LPIPS just to make sure the compressed image can be decompressed back into something that looks roughly like the original.
Right. It was never optimized for the complex semantic text-to-image generation tasks that the actual UMM is trying to do.
Precisely. And that lossy compression imposes a really rigid upper bound on quality. I mean, it doesn't matter how many billions of parameters you add to your UMM later.
And how much data you feed it.
Exactly. You just cannot overcome the limitations of that frozen external VAE. It acts as a hard ceiling on how good the generated image can actually look.
So the natural reaction for a lot of researchers, and probably a lot of people listening to this right now, might be to just remove the VAE entirely.
Right, just generate directly in pixel space.
Yeah, like recent models such as GT or simpler Diffusion, just map the text conditioning directly to raw RGB values and call it a day.
Well, the researchers tested that exact pixel space alternative as their baseline, and it perfectly illustrates this phenomenon we can call the pixel space quality gap.
Because of the cognitive load on the model, right?
Exactly. Think about what a UMM has to do. It handles highly complex text conditioning across a vast distribution of visual concepts.
Right.
So when you force a single set of weights to simultaneously learn the high-level semantic structure like understanding that a prompt asks for a cat sitting on a specific rug,
while also generating the extreme low-level high-frequency details.
Yeah, like predicting the exact RGB values of the cat's fur texture directly from a raw signal. The model just fails to do either of those tasks well.
And the GeniAL benchmark really highlights this failure. For some context, GeniAL basically tests a model's ability to follow complex prompts. We're talking object counting, spatial relationships, specific attribute binding.
It's a tough test.
It is. And without representation forcing, the baseline pixel space generation model scored a dismal 0.25 on GeniAL.
Ouch.
Yeah, 0.25. It produced totally distorted objects, incoherent spatial layouts, and it just failed to bridge the semantic gap between the text prompt and the raw pixel output.
So we clearly need a middle ground here. Relying on an external VAE latent space is a dead end for true end-to-end unification. But raw pixels just lack the inherent structure needed for the model to learn efficiently from scratch.
So the model requires a high-level representation to bridge the gap.
Exactly. And the absolute genius of this paper is realizing that the UMM already has these representations inside its own architecture.
The understanding pathway.
Yes. Every UMM has an encoder used for visual perception tasks. And this encoder is already trained to extract object identity, spatial composition, and semantic layout from observed images.
So representation forcing simply takes those internal perception representations and, well, turns them into generation targets.
Yeah.
Instead of just using the encoder to see, the model makes predicting those exact representations a native capability of its decoder.
It's a brilliant reuse of existing components.
I like to think of it like an artist painting a really complex scene on a canvas. You don't just start throwing raw paint at the center of the canvas and hope it somehow forms a house, right?
Right, you didn't end up with a mess.
Exactly. First, you sketch a pencil outline. You map out the proportions and the structure. Those pencil lines are the representation tokens.
I love that analogy.
And once that invisible blueprint is on the canvas, you paint the fine, high-frequency details over it. The blueprint guides the paint, even though the pencil marks are completely invisible in the final piece.
And that is the exact functional dynamic happening inside the transformer here. The model processes a single unified stream of tokens. The sequence basically goes like this. Text tokens, denoted as T, followed by representation tokens, denoted as R, and then finally pixel patches, denoted as P.
Okay, so T, then R, then P. And the T and R tokens are generated autoregressively, right? Just your standard causal next token prediction.
Yeah, standard next token. But the generation of the P tokens, the actual pixel patches, is fundamentally different. The authors use flow matching for the pixels.
Specifically bidirectional X prediction with a velocity loss, if I remember correctly.
You got it. Flow matching is a crucial component here. Instead of just predicting noise like a standard diffusion model would, bidirectional X prediction trains the model to predict the target data itself, so the pixels, along with a velocity vector field.
And that vector field points from a simple noise distribution toward the complex data distribution.
Exactly. And because it's bidirectional, it learns the trajectory smoothly in both directions.
Okay, so we have autoregressive token prediction happening in the exact same sequence as flow matching. But how do these different generation paradigms interact in the attention layers? I mean, just having tokens in a sequence doesn't automatically mean they inform each other well.
That's the beauty of it. The interaction happens natively within the shared multi-head self-attention layers. During the flow matching steps, the noisy pixel patches causally attend to the unmasked text and representation tokens.
Oh, because the R tokens sit right before the P tokens in the sequence.
Exactly. So the high-level structure encoded in that blueprint flows directly into the pixel generation. The R tokens act as explicit, in-context structural anchors.
Conceptually, predicting the encoder's representations makes perfect sense. But the implementation raises a pretty major technical hurdle, because the features coming out of a standard vision encoder are continuous high-dimensional float vectors.
Right, they aren't discrete tokens.
Yeah, and if you try to predict a continuous float array using a causal autoregressive next token objective, you run into severe error accumulation. A tiny numerical deviation at token position 3 will compound into a completely derailed representation by token position 50.
Yeah, that compounding error is exactly why they cannot use raw continuous regression. The training pipeline for representation forcing is highly engineered to solve this. First, they use an exponential moving average, or EMA, copy of the understanding encoder.
Okay, an EMA copy.
Specifically, they use a Dino v3 VITH plus 16 model, and they actually implement Navit-style variable resolution support.
Which is huge. For those unfamiliar with Navit, it allows the model to pack multiple images of different aspect ratios and resolutions into a single sequence.
Without having to crop them or pad them with empty space.
Exactly, which vastly improves training efficiency. But back to the EA, they use an exponential moving average because if the target representations are shifting wildly with every single batch update, the decoder will just never converge.
Right. The EMA provides stable, slowly updating continuous targets. But we still have that core problem of predicting continuous vectors autoregressively.
So how do they actually solve that?
To fix this, the authors implement online vector quantization. They take the continuous features produced by the EMA encoder and map them to a discrete codebook containing 16,384 learnable prototypes.
But wait, vector quantization training is notoriously unstable. Models often suffer from codebook collapse, right? Where the network just gets lazy and decides to use only like 50 of the 16,000 available codes to represent everything.
Yeah, ignoring the rest of the capacity entirely. To prevent that codebook collapse, they use momentum updates for the codebook vectors, plus Sinkhorn-Knopp balancing.
Sinkhorn-Knopp, that's an optimal transport algorithm.
It is. In this context, it basically acts as a rigid constraint during the assignment phase of training. It actively forces a uniform distribution of usage across the entire codebook.
So it physically prevents the model from lazily assigning all image features to just a handful of tokens.
Exactly. And through this quantization process, those continuous high-dimensional vectors are translated into a sequence of discrete token IDs.
And discrete token IDs are exactly what an autoregressive transformer is fundamentally designed to predict.
Exactly. And the continuous versus discrete ablation study in the paper is honestly staggering.
I was just looking at that. When the researchers attempted continuous regression, like literally trying to predict the exact float values of the encoder features, the Gen-Eval score sat at 0.26.
Which is barely a single point higher than the 0.25 baseline that used no representation forcing at all.
But when they switched to discrete tokens via quantization, the Gen-Eval score jumped to 0.76. I mean, what causes a 50-point gap just from quantizing the targets?
Well, error compounding explains part of it, like you mentioned earlier, but the primary driver is actually the information bottleneck effect. When you force continuous vectors into a discrete codebook, you inherently lose data.
Oh, so it acts as a filter.
Yes. The discretization forces the representations to drop the high-frequency, low-level details. The specific textures, lighting, exact color gradients, all of that is stripped away. It can only retain the dominant high-level semantic structure.
So it forces the blueprint to function strictly as a blueprint. If you try to regress the continuous features, the decoder is trying to predict the structural layout and some of the rendering details at the exact same time, which just ruins the factorization.
Precisely. The discretization achieves a perfectly clean architectural factorization between structure and rendering. The discrete representation tokens handle the semantic layout, and the flow matching mechanism handles the pixel-level rendering.
Now, there is a competing methodology out there that attempts to solve this same problem without messing with the token sequence at all. It's a technique called REPA, or representation alignment.
Right. REPA adds an auxiliary side loss on the diffusion side to implicitly encourage the intermediate hidden states of the model to match the encoder's features.
And the authors explicitly ablated their in-context representation forcing against REPA using the exact same baseline architecture, right?
They did. And the results of that ablation strongly validate the in-context approach. Adding REPA's auxiliary alignment loss only brought the Gen-Eval score from 0.25 up to 0.43.
While representation forcing hit 0.76.
Yeah, 0.76.
Yes.
It's a massive difference.
So it's basically implicit gradient nudging versus explicit structural anchors.
That's the perfect way to phrase it. Think about it. In a 1024 by 1024 pixel space, you're dealing with hundreds of thousands of dimensions. Applying a cosine similarity loss to the hidden layers is simply too weak of a signal to guide the spatial layout of those pixels.
But with representation forcing, the structural tokens physically exist in the KV cache.
Yes, the attention heads of the noisy pixel patches can explicitly query those discrete structural tokens. Having that hard scaffold directly in the context window provides a level of grounding that implicit feature alignment just cannot match.
And the performance metrics for the final, fully pixel space bottleneck-free model really prove the architecture works. At 1024 by 1024 resolution, the RF pixel model matches state-of-the-art VAE-based unified models.
It hits an overall Gen-Eval score of 0.84.
Which bumps up to 0.88 if you add an LLM prompt rewriter, which is standard practice anyway. And on DPG Bench, which specifically tests complex multi-object interactions and really dense prompt following, it hits 84.15.
So you can entirely bypass the VAE bottleneck without sacrificing top-tier generation quality.
Yeah, but while the generation quality is impressive, I think the most profound finding in this whole paper is the impact representation forcing has on the model's perception capabilities.
Oh, absolutely. The authors ran a really tightly controlled study comparing 4 variants, all trained on the exact same data and compute budgets.
They had a pixel baseline, pixel with RF, a VAE baseline, and VAE with RF.
Correct. And when evaluated on pure understanding and reasoning tasks, the pixel with RF variant actually outperformed the VAE with RF variant on 6 out of 8 benchmarks.
Which is crazy. That includes heavy-hitting multimodal benchmarks like MMMU, MME, and real-world QA. But why? Why would forcing a model to sketch an intermediate blueprint before drawing an image make it measurably better at answering complex multiple-choice questions about a photograph?
Because it fundamentally changes how the model organizes its internal representation space. Think about when a model relies on an external VAE, its perception pathway and its generation pathway are speaking two entirely different mathematical dialects.
Because the VAE latent space was trained in a vacuum, completely disconnected from the perception encoder.
Exactly. By removing the external VAE and relying entirely on representation forcing, the model is forced to tightly couple perception and generation within a single end-to-end learned representation space.
So the model's internal mathematical vocabulary for seeing a complex scene becomes identical to his vocabulary for drawing that scene.
Yes. That shared objective acts as a massive regularizer. It enriches the structural awareness of the entire neural network.
It's just such an elegant unification. But to be fair, the benchmarks weren't a complete sweep. The Pixel with RF model did see a slight performance dip on two specific benchmarks, DoCV-QA and ChartQA.
And those specific dips actually highlight exactly how representation forcing operates under the hood. DoCV-QA and ChartQA rely really heavily on precise, fine-grained text recognition.
They require exact optical character recognition, or OCR, and highly specific layout parsing of very small visual elements.
And as we discussed earlier with the information bottleneck, the vector quantization step intentionally drops fine-grained high-frequency details.
Right, because the RF representations abstract away those pixel-perfect details to focus on broad semantic layout. Tasks requiring exact OCR just don't benefit in the same way that general visual reasoning tasks do. The scaffold is built for macro structure, not micro texture.
And this reliance on macro structure also explains the author's choice for the understanding encoder itself. They ablated their DINOv-3 encoder against a SIGLIP2 encoder.
And SIGLIP2 is currently a state-of-the-art model for language-image alignment. Yet DINOv-3 was the clear winner for providing the representation targets. Why is that?
It comes down to the pre-training. SIGLIP2 uses contrastive pre-training, where it learns to match an entire image to a text caption. This often encourages the network to find a discriminative shortcut.
Oh, like if the caption says, "a dog in a park," the model just needs to find the dog's face to lower its loss. It doesn't necessarily need to map out the exact spatial relationship of the dog to the trees in the background.
Exactly. DINOv-3, however, is a self-supervised vision model. It's trained on masked patch prediction and student-teacher distillation, so it is forced to understand local spatial features and part-whole relationships without relying on any text shortcuts.
So SIGLIP2's contrastive training can sort of wash out precise spatial relationships, while DINOv-3 retains incredibly rich spatial and structural fidelity.
Right. When you are generating a blueprint that dictates exactly where physical pixels should be drawn on a canvas, spatial awareness is far more valuable than language alignment. The model needs to know where the objects physically belong.
The shift this paper represents is really massive. I feel like we're witnessing the end of modular stitched-together architectures. The whole era of duct taping a frozen, reconstruction-based VAE to the back of a language model is coming to a close.
It is a critical maturation of multimodal architecture. The separation of structural intent from low-level continuous execution opens up these massive pathways for scaling that VAE-based models simply cannot access.
And that factorization principle separating high-level intent from continuous execution leads to a fascinating hypothetical for you all to think about. We spent this entire deep dive on AI paper slop looking at how representation forcing translates text into continuous pixels by predicting an intermediate discrete visual blueprint.
Right.
But if this mechanism is this effective at translating high-level semantics into low-level continuous space, could it be applied to robotics?
Oh, that's a brilliant thought.
What if, instead of mapping text directly to continuous motor controls, a robotics model was forced to autoregressively predict a discrete physics representation token, or like an environmental state token, before outputting its continuous joint torques?
Could this in-context blueprint be the architectural key to building unified models that don't just see and draw, but physically move and act in complex environments?
Exactly. If the underlying math holds, and there is strong evidence it does, representation forcing could absolutely bridge the gap between semantic reasoning and continuous action spaces.
It offers a very structured way to ground complex physical execution in a high-level cognitive plan.
A unified representation space for seeing, drawing, and doing. Just something to think about while you're optimizing your next training run. Thanks for joining us for this analysis on AI paper slop, and we'll catch you on the next deep dive into the research.